There's been a lot of talk about the extensive use of silicon carbide in molten salt cooled as well as molten salt reactors. Having a very personal experience with silicon and silicon fluoride for my PhD work, I knew that wasn't a tremendously good idea.
My name is Dr. Stephen Boyd. I am a solid-state chemist.
What brings you into molten salt reactors when molten salts are liquid?
It's liquid, but a lot of the same behavior still actually exists remarkably, even though it's a liquid.
One interesting design for nuclear reactors is the pebble bed modular reactor. At the heart of it is the TRISO fuel unit. Here's the UO2 pellet that's inside, or pebble. And here we get to the meat of the matter. We've got porous carbon. We've got an inner layer of pyrolytic carbon. We've got a silicon carbide barrier. And we've got an outer layer of pyrolytic carbon. Why is the pyrolytic carbon used? It's because it's basically chemically inert in a fluorinating bath. However, it also has no tensile strength. There's no structural intensity to pyrolytic carbon. Here's the UO2 or THO2, thorium dioxide, that could be used at the heart of these TRISO shells. In an alternative version, you can use graphite, but again, graphite has very, very little structural integrity. In stark contrast to silicon carbide, which is used as a refractory material, which can tolerate gargantuan changes in temperature with no loss of structural integrity. However, there is a chemical compatibility issue.
Devices and materials and alloys that are used to hold the molten salts are obviously in intimate contact with the molten salts. And so that chemistry is chemistry of solids. And so that actually plays a very, very important role in thinking about the metallurgy, thinking about the material science, thinking about the atomic or molecular interactions between the solids and the molten salt.
So let's talk a little bit about the crystallography, about the structure of silicon carbide. So we look at the ball and stick figure here. I prefer to use this cartoon. Why? Because it's a tetrahedron, okay? 4 points. I like the carbon at the center, and I like the silicons on the vertices of the tetrahedron. Because carbon obeys the 8-electron, the Lewis octet rule. Silicon doesn't. So it makes the chemistry, to think about the chemistry and the interactivity of fluorinating salts with silicon a little bit easier to think about.
The challenges for molten salt reactors are containment, in situ reactivity, and high subatomic particle flux. So, right, we've got all sorts of subatomic particles bouncing around really, really fast and can really do a number on the very atoms that make up the pipes.
Silicon carbide is a very, very interesting material. It has fabulous properties. These are represented in this cartoon as solid objects, but remember, we've got silicon at the vertices, and we've got the carbon at the center, right? This is an opaque tetrahedron right now, but just think about the carbon. But now let's talk about the geometry. There's several ways we can stack these tetrahedra on top of one another. We can stack it in parallel fashion, so all the points are pointing in one direction. We can stack it in an anti-parallel fashion. Now look at what happens. There's a hole here. It represents a drop in symmetry, concomitantly, an increase in chemical reactivity potential. And so too, I will show you that we have rather interesting evidence, and convincingly so, of that.
When you're talking about getting stuff certified for nuclear use, well, the Ornell guys, they're not talking about any nuclear stuff in the molten salts. They just want to use it as a heat exchanger.
Yes.
Now, is that not a valid way of getting the ball rolling here?
There is one operating salt loop here in the United States, to the best of my knowledge. It's at University of Wisconsin-Madison. In the paper that we just got published, which I'm very excited about, we cited the work that was done actually at University of Wisconsin-Madison in that salt loop, demonstrating the fact that silicon carbide doesn't do well in a molten fluorinating salt environment, which is exactly what they were using. The salt loop that has been, I guess, partially constructed at Oak Ridge, it's my understanding that the salt loop built at Oak Ridge, which is not yet operational, is made out of silicon carbide.
So I was kind of hinting toward the different stacking motifs that could occur. And sure enough, there are quite a number of them. You can stack those silicon carbide tetrahedra in different fashions as you go up. Stack up. And these are named historically here, okay? But there are different stacking motifs. Now look, AB, ABC, ABAC, ABC, ACB. Why is this permissible? This is permissible because that tetrahedron can be stacked. It's symmetric in all directions. So it can be stacked in these different configurations, and it's nevertheless the same, okay? There are changes in symmetry, however, and those drops in symmetry translate, generally speaking, into an increase in chemical reactivity. In this particular case, this is an example of so-called polytypism. So it's chemically identical, but the stacking motifs in the crystal are actually different. In addition to polytypism, you can have alternating layers of each polytype. So now look at the patterns that we have here. So now we have almost kind of a parallel herringbone pattern here. And remember, these are all just stacking motifs of the silicon carbide tetrahedra. This robust difference and variety actually does not bode well for the chemical reactivity. Obviously, we would love to use silicon carbide in a molten salt reactor because it's got good tensile strength, okay? It's a refractory material, okay, so it can perform over a huge temperature range. And it's got a fabulously high phase change point. And oh look, we have what seems to be a very clear difference between the alpha and beta polytypes. In reality, of course, I've just shown you that that's actually not the case. And there's decades of evidence, crystallographic evidence of this. Here's the structure of silicon carbide. There's the decomposition point. But wait a second, it's not symmetric as we go up and down. It's not symmetric as we go up and down. It would be great if it were, but it's not. So there are energy differences associated with the increase and decrease. And these are reflected in the expansion coefficients. So it's expanding at a different rate. So if we're thinking, dl dt, where capital T is temperature, or per unit time, it changes. This is a Berger vector diagram, okay? The crystallography was worked out by Berger as to which motif it goes to and which direction. This is a workout of how silicon carbide changes, basically, how the screw planes, how those tetrahedra move as a function of temperature. For the physicists, including my co-author, Kevin Stone, we like to think about things in terms of band gap. So we have a rearrangement of the silicon carbide layers, and look at the band gap. Look at the energy differences here. This is definitely enough to make a difference in terms of chemical reactivity. Look at the massive change in the crystallographic C lattice constant. What does that mean in layman's terms? That means there is much more availability for chemical reactivity along the crystallographic C for that particular motif, the 6H motif. For us, this is what drove the argument home. We use X-rays to look at crystals, to figure out those structures, okay? And it's like a fingerprint. We have the alpha peak. These are called reflections in 2 theta. And we have the beta. Nishimura, a researcher out of Japan, did this work. Did it with FLIBE and the different polytypes of silicon carbide. Did it at temperature, so 587 Celsius. Okay, so actual FLIBE, silicon carbide, 2 different polytypes. So this is his baseline, right? This is his control, okay? After only 1 day of exposure to FLIBE at 587 Celsius, look at the difference. The beta polytype reflection is gone. It's dissolving. It's actually dissolving. Now, we have a lot more evidence. We have actually 50 citations in our paper. And in fact, some of the citations came directly from Per Peterson's research out of the University of Wisconsin-Madison. Because Luke Olson, the PhD candidate who has now gone on to get his PhD and is now a postdoctoral fellow, actually found silicon fluoride residue in the molten salt loop that he was working with. Now, one could argue, okay, fine, the molten salt that he was using was not fluoride. It was actually more caustic. It was FLINAC. It was more caustic than fluoride. So now, after 1 day of dipping, we already have a change in 2 theta for the beta. After 3 days, oh, wait a second, now we have the emergence of other peaks. So we have in situ shifting, and then after 10 days of dipping, all of your crystallinity is going away. So it's actually dissolving.
A two-fluid reactor would mean that inner tube, you've got stuff going around, and the outer tube, separated by a wall, has got more thorium tetrafluoride. You've got a tricky chemistry and physics problem here. You've got to keep those two things separate, so you've got to think a lot about that wall. What goes into that wall? You also have to let the neutrons through in order to make the thorium go into the uranium-233, the unusual isotope of uranium-233, which is fissile, which is how that works. It's how that goes forward. Nobody knows what material that can currently be made out of.
Can't be graphite?
Cannot be graphite. When you take on neutrons, graphite swells. Also, graphite is not a structural material. It'll fall apart. It doesn't have any structure to it. You can't build a building out of glass, right? You can have glass in the windows, but the windows aren't serving any structural purpose. And so you need a material that will serve as a structural material, can tolerate the extremely high neutron flux, the extremely high heat, and you're in a two-sided molten fluorinating salt environment. That's weird. That's really, really tough. So I would assert that you can't currently do it. Part of the reason why we wrote the paper that we wrote was because silicon carbide was being thrown around. I would assert, though, that there is plenty of evidence out there that would not support the use of silicon carbide as that special wall material.
The rich variety of silicon carbide in terms of its crystallographic structure is actually a liability. As much as I personally, as a solid-state chemist, would love to use silicon carbide, we can't use it in a molten salt because they dissolve. Okay? The fluorinating baths dissolve, and there is unbelievably conclusive evidence right there after only 10 days at 587 Celsius. So even cursory exposure to fluorinating molten salts is very, very bad for silicon carbide integrity. In the paper, we actually cite some work by a very good condensed matter physicist named Natalia Baklanova, with whom I've communicated several times. She's out of Novosibirsk, and she's got some excellent carbon composite alternatives. So for future work, I would love to get my hands on some DFT modeling, and I would love to model extensively with alternative materials such as titanium carbide, this should be a slash, carbon-carbon composites such as TKM, as well as M, where M represents a metal carbide composite hybrids, and functionalized carbon scaffolding. So space-based or terrestrial nuclear reactors design must consider alternatives to silicon carbide if they're going to be taken seriously. And we cite several pieces of ongoing work, actually by Charles Forsberg and Per Peterson, that find silicon carbide residues in their molten salt loops, post-mortem.
Blow your mind.
So again, thanks to Kim Johnson. He's got some excellent chemistry that we have in the paper that he worked out. And thanks to Kevin Stone and Dr. John Palumbo, who was unable to attend. But we're very pleased that we've gotten published on this paper. And we want to do future work.
Shifting, you're saying purely a thermal effect as it goes through phase change?
Was it a thermal effect or was it a chemical effect? It's a neutronic effect as well as a chemical effect. So the dissolution of the silicon carbide crystal lattice is a direct result of the chemical reactivity with the fluorinating salt. But the neutronic effects are also very interesting. When I gave my talk at Los Alamos in February, a very interesting fellow came up to me and started speaking to me, and he actually did neutronic simulations on silicon carbide and found something very interesting that I didn't know about. After 4.6 years of thermal neutron flux exposure, the silicon turns to magnesium. And if anybody knows anything about magnesium carbide, it's not stable. It's not stable. There are some tropes that are stable, but not the ones that end up in here. They couldn't actually get a stable trope of magnesium carbide as a direct result of neutron flux exposure and the change from silicon to magnesium. So, yeah, very, very interesting. So it's going to fall apart from the inside or the outside, either way. They did not get funded, by the way, at Los Alamos. He and his wife are both physicists. They're both excellent researchers. They did that on the weekends by themselves. That was impressive because that was a really sexy question that they wanted to answer, and they answered it.
Do you expect any reaction soon from Per Peterson?
No.
The short answer is no, because I cited his own work. I cited Luke Olson's own work.
He just showed that his three-cell pebbles ain't going to work.
And that's true, but I didn't have to show him that because I pulled, if you notice, some of the earliest citations are from 1968, before I was born. So I don't know what to...
It seems odd.
It does seem odd.
Do you think that other carbides might have similar effects like titanium carbide?
Yes, it's possible. Okay, so titanium carbide in and of itself will definitely not work. It'll be highly reactive. However, what Dr. Natalia Baklanova in Novosibirsk has been working on, and as well as other researchers, mostly physicists in Russia, have been working on carbon-carbon composites, and basically using carbides as kind of a mesoscopic glue in between the carbon fibers. So long as there's no actual exposure, it provides the structural integrity that you would want and the chemical non-reactivity that you want. And of course, using materials, clever materials like the carbides with metals, for example, like titanium, which won't have a problem with the absorption of neutrons, great. That might work. But still, there's a lot of research that needs to be done.
Very good. Thank you, Stephen. Thank you very much.